when the voltage was high, a lot of them jumped from one electrode to the other, and of course they was able to be viewed with the naked eye. Okay, if you have a television that's not an LCD or plasma TV, a regular projection television, you often hear them called CRT TVs, and that is absolutely because they are composed of a cathode ray tube television. So if we look at a side panel of a TV, okay, here's our screen. Okay, here's our TV, and it sort of comes down like this. Okay, what happens is we have an electrode on the back of the TV, and there's essentially a cathode ray tube that makes up the bulk of your television. The screen has molecules that are sort of known as phosphors, and all they are going to do is when an electron or a cathode ray strikes them, they're going to emit light. Okay? So what happens is if you apply a voltage to this electrode in your TV, usually you keep the screen at ground or a low potential, and you can sort of fire electrons at your screen. When the electron hits the screen, they light up, and of course you can produce an image. Okay? We now know that electrons are negatively charged, so usually I'll just write E with a negative in the superscript to note that I'm talking about an electron. Okay, so the first thing is we could ask is two questions. One, how do we know they're negatively charged, or how did J.J. Thomson discover that they were negatively charged? And then of course, by asking that question, we can answer the same thing. How do we aim electrons at the bottom of the screen or the top of the screen to produce an image, of course, where we want, or an image of what we want? Okay. And here are the results of the experiments that do the same thing, and we can illustrate that here. So if I have an electrode here, and if I have the end of the cathode ray tube, or say our TV screen here, and I want an electron to travel to the top of my screen, what I can do is I can add additional electrodes here and maybe put a positive charge on this electrode. Or excuse me, if I want this, if I want the electron to travel to the top of the screen, I'm actually going to want a negative charge here, or I can put a positive charge at the top. Okay, so let's just keep this, put a negative charge here. Okay, so we know that these two, an electron with a negative charge and this electrode here with a negative charge, the like charges are going to repel. So instead of the electron going straight towards the middle of the screen, it's going to be repelled to the top of the screen. Okay, if I want to aim a electron at the bottom of the screen, what I can do is I can put a positive charge on that electrode, and of course the positive charge would attract the electron towards the bottom of the screen instead of repelling it. Okay, depending on how much positive or negative charge I use, I can sort of figure out how much force I need to push this electron away from this electron. Now, just like it takes more force to push a bowling ball off the table than it takes to push a tennis ball, the more force or potential that I need, we can determine how much mass this electron is. And J.J. Thomson was able to calculate the charge to mass ratio for this particle. The electron was negative 1.76 times 10 to the 8th coulombs per gram. And which was much, much, much smaller than initial experiments that the charge to the mass ratio for the hydrogen ion, a hydrogen with a positive charge on it, was 9.58 times 10 to the 4th. So much, much smaller, or excuse me, the charge-mass ratio was much, much lighter than the charge-mass ratio for our lightest element, hydrogen. So we knew the electron, or this cathode ray, was really small, and so it wasn't an element itself. It must therefore be a subatomic particle, a component of the atom. Okay. Another experiment that worked on these newly discovered electron was a famous experiment done by Robert Milken, and which is usually called his Milkens oil drop experiment. Okay, so what he did here was he sprayed oil droplets into this experimental apparatus. And an atomizer is able to spray very, very, very fine droplets. And I sprayed them at a positively charged plate with a very small aperture opening in the center of that plate. So some of the droplets could get through. Okay? He was able to impart a charge on these droplets when they were coming here with an ionizing radiation. And so by adjusting the bottom of this apparatus, which had a negative charge, and the top of this apparatus had a positive charge, he was able to levitate these charged oil droplets in the center of this apparatus. Okay? So, you know, put a negative charge on this oil droplet, repel it up with a negative charge, pull it up with a positive charge, and by adjusting that correctly, he could levitate it in the middle. Then he would look at the sphere, calculate the surface area of the sphere just by viewing it and doing a little bit of math, and he would be able to calculate the mass of that oil drop and determine the amount of charge needed to keep that size oil drop floating. And he always got to multiples of negative 1.6 times 10 to the negative 19th coulombs. Okay, so from that he was able to infer that the fundamental charge of an electron is negative 1.6 times 10 to the minus 19th coulombs. And I just saw that there's a mistake down here, so that's minus 19th coulomb. Okay, because J.J. Thomson knew the charge per mass ratio of the electron, and Milken just figured out the charge on the electron, able to determine the electron has a mass of 9.1 times 10 to the minus 28 grams. Extremely small and much smaller than the mass of our lightest element, hydrogen. Okay, so what he did was J.J. Thomson, with that and Milken's, with his and Milken's experiments, was able to propose the first hypothesis for what the structure or what the atoms look like. Okay, so we know that the atoms are no longer just indestructible. They have subatomic particles known as the electron. We know they're negatively charged, but the entire atom is charge neutral, so there must be something involved in the atom that has a positive charge to keep it neutral. So he proposed a model where the electrons sit in a sphere of positive charge, that what kept the electrons in most of the time, and this was known as the Plum pudding model. Okay. One of the true tenets of this was that the electrons are floating in this sphere, not really any matter, and so that the atom is mostly empty space because, you know, the electrons sort of stay apart because of repulsion. Okay, so we almost have our full understanding of the internal structure of the atom. Just one more classical experiment to talk about, and that was conducted by Ernest Rutherford. Okay, what he did was he wanted to probe the internal structure of the atoms to figure out if J.J. Thomson's plum pudding model was correct. And so what he did was he was able to utilize alpha particles, which are positively charged. They actually have two positives, but anyways, they're positively charged radiation from radioactive material that Marie Curie and Henry Becquerel just recently discovered. So what he did was bombard a very, very, very thin, micrometer thin piece of gold foil with these alpha particles. And he sort of encircled the gold foil with another phosphor screen that, again, just lights up when something energetic strikes it. Okay? And what he saw was most of the time the alpha particles went straight through the gold foil because it was so thin, and the proposed mechanism for the atom was mostly empty space. So this is what they were expecting, most of the alpha particles, if not all of the alpha particles, to go right through. Okay? Some of their more surprising results were that some of the alpha particles were deflected at large angles. Okay? And even smaller amounts, but still surprising and still very amazingly, some of them come back almost straight at the source or very small angles. Okay? And again, those second and third results were very surprising to Ernest Rutherford and his research group. Okay? So what's going on here? So let's take a look at their alpha particles, which again are positively charged. And now we have our thin gold foil sheet. Again, because the atom is mostly empty space, most of the outer particles, around 99%, went straight through. Okay, some of the alpha particles were deflected to large angles, as I said. And let's say this is around a little bit less than 1%. Okay, a very small percent were deflected back to small angles, and this was around 0.1%, so very small percentage. Okay, so what they realized, and through these experiments, is that the atom was mostly empty space, but there was something there that these alpha particles were striking. And if you imagine something in the middle, which we will explain why we now know it's positively charged in the middle, well, of course, the large angle deflections, about the 1%, these guys, these were alpha particles that came close to this structure, and because it is positively charged, were repelled, just like our electron was repelled when we wanted to aim it at our screen. And a very small percentage of these alpha particles made a direct hit at this structure in this atom. And we now know that this is the nucleus of atoms, and it contains protons, which of course are positively charged. Because most of the alpha particles went through, we still confirm that the atoms are mostly empty space, but they do have this very important structure in the middle known as the nucleus. And so Ernest Rutherford came up with a new model of the atom, or a theory, atomic theory, improved upon John Dalton's explanation through experimentation. And he said that, of course, the atoms contain a tiny dense center, which he termed the nucleus. Now, because of the ratio of the alpha particles that came back to the ones that got through, they knew that the entire space of the atom is mostly empty space, or electrons, and the nucleus only takes about 1/10,000,000,000th of the volume of the atom. Okay? Because the electrons weigh so little, they give almost no mass to the atom, so the nucleus has essentially the entire mass of the atom. Okay? We also know that the nucleus is positively charged because of the large angle reflections, because of repulsion. And the one thing that J.J. Thomson got right was the electrons are dispersed in the empty space of the atom surrounding the nucleus.